Welcome to Module 2, Units, Dimensions, and Measurement. In building automation, every point, trend, calculation, and control decision depends on measurement. A value like 25 is meaningless until we know whether it is 25 degrees Fahrenheit, 25% relative humidity, 25 psi, or 25 kilowatts. This module teaches learners to protect engineering decisions by preserving units, understanding measurement quality, and checking whether BAS data is fit for the decision being made. In this module, we are not trying to memorize every possible conversion. We are building a professional habit. Every engineering value must carry a unit, a range, an accuracy, and an intended purpose. By the end, learners should be able to look at a BAS point and ask, what is the unit? Is the scaling correct? Is the sensor appropriate? Is this value accurate enough for the decision I am making? This slide gives the big picture. The BAS does not begin with software. It begins with a real physical condition. A sensor detects that condition, produces a signal, the controller scales the signal into engineering units, and the BAS uses that information to monitor, control, alarm, trend, and optimize. If the unit, range, scaling, or sensor quality is wrong, the decision can be wrong even if the graphic looks professional. This chapter begins with a simple warning. A number without a unit is not an engineering result. The value 25 can mean many things. In a BAS, that mistake can appear in graphics, sequences, meters, integrations, and reports. A pressure point configured in pascals, but compared against inches of water column can drive a fan incorrectly. A meter reporting watts while the graphic assumes kilowatts can distort energy reporting. Unit governance is a professional control. Temperature conversion creates a common field mistake. A temperature value and a temperature difference are not converted the same way. A value of 20 degrees Celsius equals 68 degrees Fahrenheit, but a difference of 20 degrees Celsius equals a difference of 36 degrees Fahrenheit. In heat transfer equations, the difference is what matters. That distinction protects the calculation from a major error. Power is the rate at which energy is transferred or used. Energy is that rate accumulated over time. A chiller input of 100 kilowatts is a power value. If it runs at 100 kilowatts for 4 hours, it uses 400 kilowatt hours of energy. This matters in BAS reporting, demand management, utility analysis, and savings verification. Dimensional analysis is one of the fastest ways to find a calculation problem. The method is simple. Write every value with its unit, apply the equation, and confirm that the units cancel to the expected final result. If you calculate heat transfer and your units do not reduce to BTU per hour, something is wrong. This protects learners from mixing minutes with hours, watts with kilowatts, water equations with airflow equations, or temperature values with temperature differences. These terms are often used casually, but they are not the same. Accuracy tells us closeness to truth. Precision tells us whether repeated readings agree with each other. Resolution tells us how fine the display or input can represent the value. Repeatability describes consistency. Drift describes change over time. Uncertainty describes how confidently the measurement can support a decision. A sensor may repeatedly report 75 degrees even when the true value is 72 degrees. That sensor is precise but inaccurate. A BAS display can show many decimal places, but that does not prove accuracy. If a room sensor is accurate to plus or minus 0.5 degrees Fahrenheit, displaying 72.000 degrees gives the learner false confidence. Energy analysis has the same problem. If the input values are estimated, the result should not be reported with excessive digits. The display should match the quality of the measurement. This worked example from the chapter is important because many BAS professionals confuse resolution with accuracy. A 12-bit input can represent very small increments, but real measurement quality is affected by transmitter accuracy, tubing, pressure pickup location, electrical noise, input performance, scaling, and calibration. A tiny displayed increment is not proof that the real process is known with that precision. The manager's note in the chapter reminds us that many BAS database problems are unit problems. A point may be mapped to the correct equipment, but labeled incorrectly. A meter may report watts while the graphic assumes kilowatts. A pressure transmitter may be configured in pascals while the sequence compares it against inches of water. The professional response is not to trust the graphic. It is to verify source unit, scaling, label, range, trend history, and the decision logic that uses the point. These are the recurring mistakes the learner should watch for. The goal is not to shame mistakes, it is to create a repeatable professional habit. Preserve units. Know whether a value is a rate or a total. Never confuse resolution with accuracy. Do not apply field constants outside their assumptions, do not publish false precision, and do not let a graphic label become the only evidence. The practical assignment is a measurement quality audit. Learners should select 10 BAS points from a real or sample system. For each point, they record the unit, range, scaling, accuracy, calibration status, location, and the decision that depends on it. Then they identify the 3 weakest points and explain what should be verified before those points are used for control, reporting, or optimization. To close the module, reinforce the major point. The BAS depends on measurement. Units, scaling, accuracy, uncertainty, and assumptions are not paperwork. They are the foundation of control quality. In the next module, learners will use these measurement habits to evaluate energy, heat, work, and thermodynamic behavior in HVAC systems.